In this video, I'll be going over polynomial inequalities. To start, we'll be looking at quadratic inequalities. And a quadratic inequality is just something that is quadratic in form, and instead of having an equal sign, it has an inequality sign. So something like x squared minus 4x minus 5 is less than 0, or maybe something like negative 1/2 x squared plus 4x minus 7 is greater than or equal to 0. Notice that each of these are quadratic in form, and we have an inequality symbol right here. Okay, so what we want to do is, in general, what this is saying is, when does this quadratic expression, when is it less than or equal to 0? And the second quadratic inequality is saying, when is this quadratic expression greater than or equal to 0? Now, one way we can do this is by looking at a graph. So suppose we had a quadratic function, a quadratic function that we graphed, and it looked something like this. Remember, a quadratic function is going to be a parabola. Now, if we wanted to know when is this quadratic, let's say, greater than 0, well, greater than 0 is in this section up here. This is when the quadratic is above the x-axis. So what we'd do is we'd say these x values in here tell us when the quadratic is above 0, and furthermore when it's greater than 0. Okay? On the left portion and the right portion of this this graph, that's where this quadratic function is negative. So in this portion and in this portion, that's when the function is less than 0. Okay, so to solve a quadratic inequality, we want to find out when the function equals 0, and then we just determine the intervals that will give us positive and negative values. So let's look at a couple examples of this. Alright, so our first example says to solve the quadratic inequality, x squared is greater than 4x plus 5. Now, the first thing we always want to do on these types of questions is get all of the terms to one side. So I'm going to subtract 4x, subtract 5, so I end up with x squared minus 4x minus 5 greater than 0. Okay, so I think this is actually the first sample that I gave in the previous slide. So what we want to do here is we want to find out when is this expression greater than 0. Now, to do this, we want to find out when does this quadratic equal 0. So to find out when this equals 0, I'm going to set it equal to 0 and solve this equation. I can solve this by factoring x minus 5, x plus 1. Okay, so I get x is equal to 5, x is equal to negative 1. So what that tells us is those are the values when the quadratic is equal to 0. Now, what you want to do is graph this quadratic function. Okay, and we don't have to be super precise here. What we need is where are the values that the quadratic is going to hit the x-axis. So it's going to hit at 5 and at negative 1. And then because the leading coefficient here is a positive, that means this quadratic is going to be opening upward. So if I get a rough sketch of this, and again, it doesn't have to be super precise. I don't really need to know, I don't even need to label the y-intercept. I'm just really focusing on the x-intercepts here. Okay, so what we can see is that this quadratic, or this parabola, is above the x-axis over here. So in these x values, from negative infinity up to negative 1, that's going to give me values for the quadratic that are positive. And it's positive because on the left-hand portion of this graph, the graph is above the x-axis. Between negative 1 and 5, this is going to be negative because, as you can see, the graph is below the x-axis. and then to the right of 5 it's going to be positive. So we see that we have 3 separate intervals here. We have the interval from negative infinity to negative 1, and we don't include negative 1 here, and we'll talk more about that in a sec. We have the interval from negative 1 to 5, and then we have the interval from 5 to infinity. Okay, so our original question was, when is this greater than 0? Another way of thinking about this is, when is this quadratic positive? And it's positive in the interval to the left and the interval at the right. So our answer here, which we'll give an interval notation, is negative infinity to negative 1 union 5 to infinity. And I just want to circle back to why we don't include the endpoints on these intervals. The reason is because the original inequality was greater than 0. So because this is saying greater than 0, at the endpoints of these intervals, at negative 1, the function is actually equal to 0, and at 5, the function is equal to 0. So when we have a greater than 0, we're going to use parentheses. But if we had greater than or equal to 0, we would use the square brackets on the interval, because if it was greater than or equal to 0, we would be including those endpoints, because those endpoints tell us when the function is equal to 0. Alright, so we have another quadratic inequality. We have x squared plus 3x minus 5 is less than or equal to x plus 3. So just like the last one, we want to set this less than or equal to 0. We want all the terms to be to one side, so this will be x squared plus 2x minus 8 less than or equal to 0. It's kind of like we're solving this equation, x squared plus 2x minus 8 is equal to 0, because we want to know, when does this function equal to 0. I forgot an x in there. So x squared plus 2x minus 8, when I factor that, I'm going to get x plus 4, x minus 2, so I'm going to have x is equal to negative 4, x is equal to positive 2. Okay, so graphing this, I'm going to have x-intercepts at negative 4 and positive 2. This quadratic is still opening upward because I have an a value of positive 1 here. So it's going to look something like this. Now, because I want to know when this is less than or equal to 0, I'm going to be using the intervals, let me back that up here. Less than or 0 is the inside portion here. Okay, so that interval is negative 4 to positive 2, and because the inequality is less than or equal to 0, I want to include those endpoints. Okay, so there's our answer. And then again, let's just talk about what the solution to an inequality actually means. Well, what this is saying is, if I plug in a number anywhere between negative 4 and 2, and if I include those endpoints, any of these numbers, if I substitute it into the original inequality, or this version of the inequality, it doesn't matter, but if I substitute any value from negative 4 to positive 2 into that inequality, that will make a true statement. Okay, so that's how you can check your answer. So how about I just substitute in positive 1? Let's see what happens. So if I plug in 1, I get 1 squared, which is 1, plus 3 times 1 is 3, minus 5, and that's less than or equal to 1 plus 3. So on the left hand side I get 1 plus 3 minus 5, which is what, negative 1. And on the right hand side I get 4. So negative 1 is less than or equal to 4. That's a true statement, so that tells me that the value of 1 works, and likewise any other value in that interval would also work. Alright, so now let's expand from just quadratic inequalities to a function of any degree, not just degree 2. So a similar idea is going to be at play here. So suppose I had a polynomial function and its graph looked something like this. Okay, and I wanted to know, and let's say that this is f of x, and I wanted to know when is f of x, let's say, greater than 0. Well, in this interval, the value of the function is going to be negative, and then it's positive, and then negative here. It just bounces off of 0 here, so then we're negative again over here, and it equals 0 at that point. So when is the function greater than 0? Well, it's going to be from this point to this point. That's where it's positive. So that's the idea with these polynomial inequalities. We want to find the values that make the function either positive or negative, and sometimes equal to 0. So a couple of examples of something like this, maybe negative 2x to the fourth plus x squared minus 3 is less than 7. Notice that this is not a quadratic, but we're going to solve this in much the same way as we did with the quadratics. 4x cubed minus 2x squared greater than 5x plus 7. So the idea is the same. We get all the terms to one side, set it to 0, and then from there what we'll do is we'll graph and then find the intervals where it's either positive or negative. So let's look at a couple quick examples of this. So we have x cubed minus x is greater than 0. So I'm going to first I'll set this equal to 0, and then I'm going to factor this. I can factor out an x. I'm left with x squared minus 1, and then x times x plus 1, x minus 1 is equal to 0. So I'm going to get x is equal to 0, negative 1, and positive 1. So those will be the intercepts of this function. So when I graph this, the function is going to hit the x-intercept at 0, positive 1, and negative 1. The leading term is positive, so I'm going to end up in the positive direction because the degree is 0. I'm sorry, it's not 0. Because the degree is odd, that means I'm going to start in the opposite direction. So the function, the graph of x cubed minus x will look something like this. And I want to know when is this positive because it's greater than 0. So this function is positive, it looks like when we are in this interval and then over here. So the solution intervals are going to be net from negative 1 to 0, and I'm not going to include those because my original inequality, which is greater than 0. So negative 1 to 0, and then union from 1 to infinity. And that's it. Alright, we'll look at one last example here. We want to solve x cubed plus x squared is less than or equal to 7x plus 3. Now the issue with this one is that when I set this less than or equal to 0, I get a cubic function, x cubed plus x squared minus 7x minus 3. Now the issue here is that this is not easily factored. So when I'm left with x cubed plus x squared minus 7x minus 3, and I set that equal to 0, factoring isn't really going to help me here. And so the strategy that we use is something called synthetic division. So I take the coefficients of each term. So the coefficient on x cubed is 1, coefficient on x squared is 1, and then negative 7 and negative 3. And I'm going to do synthetic division to see if I can reduce this from a cubic to something that is quadratic. Now, the numbers I want to test in here are going to be 1, negative 1, 3, negative 3. And the number I'm going to test first is negative 3. Actually, let's test 1 just because that's easiest. So how we do this is we always bring down the first number, 1, and then what we do is we multiply this 1 times this 1, which is 1, and then I add the two rows together. So 1 plus 1 is 2. 2 times 1 is 2, and then add, I'm left with negative 5. Negative 5 times 1 is negative 5. Adding, I get negative 8. I'm hoping for a 0 in this position. Okay, Now, because I didn't get a 0, that tells me that 1 does not divide evenly into the original cubic function. So what I need to do is I need to test a different number. So I'll test negative 3. Again, we always bring down that first digit. So 1 times negative 3 is negative 3. Adding this together, I'm left with negative 2. Negative 2 times negative 3 is positive 6. I'm left with negative 1 when I add, and then negative 1 times negative 3 is positive 3. Then I'm left with a 0. So that's great. Okay, so what this means is my new function is 1x squared minus 2x minus 1. Okay, and so that is, I don't need to write that in parentheses necessarily, but that is going to be equal to 0. So now to solve this quadratic, we know how to do that. This one doesn't factor, but I can use the quadratic formula. So x is going to be opposite of b, so opposite of negative 2 is positive 2 plus or minus b squared, which is negative 2 squared, so 4 minus 4ac all over 2 times a, which is just 2. I have 2 plus or minus the square root. Under the radical, I'm going to get positive 8 divided by 2. Simplifying this, I'm going to have 2 plus or minus square root of 8 simplifies to 2 square root 2. And then each of these 2's can be divided by 1. So I'm left with 1 plus or minus the square root of 2. Okay, so those are two of the values, one positive, one negative, that x is equal to. And then when we go back to what we found with the synthetic division, this negative 3, that's telling us that x is equal to negative 3 is the other 0, okay? Or the other x-intercept. So graphing this, I have an x-intercept of negative 3, and then I have one value that's 1 plus square root of 2. Then I have one value that's 1 minus the square root of 2. And 1 minus the square root of 2 is about negative 0.4. So I'll put that in here. 1 minus square root of 2. Okay. So what this graph is going to look like, again, x cubed, I look at that leading term, it's odd, so I'm going to start in one quadrant and end up in the opposite quadrant. The leading coefficient is positive, so I'm going to end up going up. So something like that. This is actually the same general shape, same end behavior as the previous example. And because this is less than or equal to 0, I want to know when is this graph either equal to 0 or below the x-axis. So it's, or in other words, when is it negative? It's negative here, it's negative in this interval. So my solutions are going to be negative infinity to negative 3. I include the negative 3 because we're less than or equal to. And then union, I'm from 1 minus root 2 to 1 plus root 2. And that is the solution.